All right, so shortened week. Welcome back from your break. Remember that you don't have an assignment this week, but next week you've got programming assignments on graphs and graph algorithms. So that's where we'll pick it up. That's where we left off last time. We were looking at a depth-first search traversal. Now, you're well familiar with depth-first search already because you've seen them before in terms of trees, right? A depth-first search, as the name suggests, just searches as deep as possible before backtracking and going to other nodes in the graph. Now, in terms of a tree, when it's highly structured, right, that means that you're going as deep as possible into the left subtree before you visit the right subtrees, right? And so the tree traversal algorithms like in order, pre-order, and post-order, those are all DFS with just different order on the criteria on when you actually process a node in the tree, right? Otherwise, when you do a DFS search on a general graph, you want to make sure that you're not, getting stuck, right? If I go, let's go ahead and bring up that graph that we were looking at on Friday to remind ourselves of what it looks like. There we go. You want to make sure that you're not going to get stuck in a loop, right? That if you just go ahead and go as deep as possible into the tree, you want to make sure that, well, okay, I've already visited I, so I'm not going to go there again. Otherwise, I would get stuck in this loop, this infinite loop, if I just keep going around forever, right? So you want to make progress towards the end, right? You want to make sure that you don't enumerate every single possible path. You want to make sure that you don't repeat a node or a path too much. Now, it could be that you see a node and you say, I've been there before. That's perfectly fine to do that, but you don't go to that node more than once. You don't process a node more than once. Now, this is in contrast to, if you remember back to your first assignment, when we were doing brute force algorithms, you had to do a Hamiltonian path or Hamiltonian cycle. Which one was it? Path, right? There you were enumerating every single possible path. Because you wanted to find a particular path with a particular property that it visited every node exactly once. Here we don't want to do that, right? Because that would be exponential, right? We don't want to process everything more than once, right? So we're only going to visit things more than at most once. The strategy again is to go as deep as possible before we start backtracking. And along the way, what we did on Friday was we kept track of other ancillary information. In order to ensure all of these properties. Have you visited this node before, right? Have you seen this node before? Have you processed this node before, right? When did you first see this node? And when did you process the vertex? Each one of those answers was with colors, right? We used colors to indicate state, right? That white would be unvisited. Gray, EI or AI, gray would be visited but not yet processed. Right? And then finally black would be visited or processed. Processed, done. Right? Now, the reason that they use white, gray, and black is because traditionally if it's going to be printed in a textbook, right, color printing is expensive. So how do they distinguish between these three states? White, black, and gray, those are the cheap colors to use. Now, when I was doing it over here on the iPad here, I was using whatever my my highlighter colors were at the time, right? And of course, if you've got a colorblind audience, you don't want to use any colors that are difficult to distinguish between each other. If you're actually going to program something like this, don't use white, gray, black. Use word descriptive terms, right? Unvisited, visited, and processed. All right, that's what I would do. All right, so we need to develop our algorithm. Let's talk about the actual algorithm. Right? So you can develop a recursive version. Right? That is, you're at given the current node, right, you need to decide which node to visit next. ... Okay, so let's take a look at a generalization of that right over here. So suppose that I'm in this current node, and I'll just go ahead and name that U, right? I came from somewhere, right? I came, explored the graph at some point, and now I'm at this current node. What I need to do is I need to look at the neighborhood of U, right? The things going out of it. This is the neighborhood of U. Right? Neighborhood. Right? And I need to make a decision on which one do I go to next. Well, first of all, if it's a white vertex, white, that means it's unvisited. All right? I may want to go there next. What if I look at a gray vertex here? Gray. Do I want to go to that vertex next? No, because that means that I have visited it, but yet not processed it, right? And I don't want to go there next because I've already, it's either probably in my breadcrumbs of how I got here, right? That might be one of the things that that immediately brought me to this state, or it's just that it's some other node that's been visited but not yet processed. What about a black node? And for that, I'll just fill this in all the way. There we go. Probably not that either because it's already been processed. Why would you go to that node again if it's already been processed? Why would you go to this node already if it's been visited, just it hasn't been processed yet? Right? So in other words, and here, let's go back to the notes here. You need to decide which node to visit next, right? Only consider unvisited, that is, white nodes, right? Okay? And then choose the next one, right? And the way that you do this is you color the current vertex gray. That is, you've visited, but not yet processed the node, right? And then you make a recursive call to the next available white node, right? White unvisited node, right? Using some criteria. Now, the criteria that we used on Friday was what? If you're going to label these nodes with letters, just go in lexicographic order, right? What's an alternative? Random. What's another alternative? If there were weighted edges, you could go to the least weighted edge next. You could go to the highest weighted edge next. You could go in lexicographic reversed order, right? Whatever criteria you're going to use, right? Using some criteria. This is lexicographic or edge, weights, etc. Right? Whatever criteria you're going to use, that's when you decide that criteria. Look at the neighborhood, right? You only consider unvisited white nodes in the neighborhood hood of the current vertex, right? Of the current vertex. And then you choose the next one, right? On your way back, if no such unvisited visited vertex exists, or if you have then visited them all in the neighborhood, you process the current node, right? That is, color it black, output it, etc. Whatever you're going to do, whatever process means, right? You're just going to enumerate the vertices, right? And then you return, and then return. Okay? So that's the recursive version of this, okay? Now, when we looked at tree traversal algorithms in, say, 156, we did essentially this, right? The pre-order, post-order, all it was is visit the left, then visit the right, and where do you process the node? Do you process it before, between, or after, right? And that gave you a pre-order, in-order, and post-order traversal. And there were only two calls to visit the left subchild or the right subchild because it was a highly ordered tree. Here, you have an entire neighborhood to consider, right? So your neighborhood in a tree is a left child and a right child and then the parent, but that's where you came from, so you ignore it. That would have been colored gray. You go to the left child, you go to the right child, you come back up, and then you return, right? So it's exactly the same thing as one of those pre-order, post-order, in-order traversals. It's just that your choices are much less limited. Now, we probably looked at a recursive version in 156. Did we ultimately use a recursive version, or did we use a better version? So smart data structures, and one of the themes of 156, Computer Science 2, is smart data structures and dumb code are a lot better than the other way around, right? So what kind of smart data structure did we use? Do you remember? Well, let's look at this as an example. Remember our DFS on Friday. We went to A, then to B, then to C, D, E, F, right? Now this highlight that I've got right here, that's keeping track of where I've been, right? This is the breadcrumbs so that I can go back to where I came from, right? I can find my way back. So think breadcrumbs here. How do you keep track of these values here? What if I wrote them all in a list of some sort? I, A, B, C, D, E, F. There we go. Now, what if I, oops, no, I want it the other way. What if I did this? Drew it as kind of a list, and let me visualize it even further by moving this up over here. Right, there we go. Come on, copy, or actually cut and paste. And what if I visualized it like that instead? What is that thing? It's a stack. Stacks can be used, I mean, when you're doing a recursive version, what are you using? You're using the call stack, right? And you are abusing the call stack because you're letting the program stack do all your work for you. Let's do our own work here, okay? And let's go ahead and think of a stack-based DFS, right? So stack-based DFS. So suppose that we're at a current vertex. The top of the stack holds the current vertex. Right? Let me see. Let me make sure. Yep. The current vertex. We pop it off the top of the stack, right? And we look at its neighborhood. All unvisited visited vertices are colored, are placed into the stack, right? Or no, it's not all unvisited. Among all unvisited, that is white vertices, you choose the next one. Actually, no, we don't pop it off. We peek at it, at the top of the stack, I should say, at the top of the stack. There we go. Among all unvisited vertices, white vertices, you choose the next one and push it onto the stack. Right? What if you don't have any more? If none, you start backtracking. And at that point, you start popping things off the top of the stack. Okay? So let's take a look at an example here from last time. Let's go ahead and get rid of all of this stuff right here. Right? And what we're going to do is we're going to initialize a stack here. There we go. Nice clean stack. And we'll go ahead and start at I. Right? So I'm going to go ahead. But I'm also going to keep track of some other things. All right? So here are statistics. Artifacts is what I want to call it. Artifacts. We're going to consider the color of the vertex. We are going to consider the discovery time, just like we did on Friday, and the end time, the process time. Now, with respect to a stack here, the discovery time is going to end up being when you first see it and you put it into the stack. That's when you go to it, right? Right? Yeah. And then we're also going, once you put it into a stack, you're going to color it gray, right? So colors. Initially, initialize, everything is going to be white, unvisited. Right? Then the first time into the stack, it's going to be colored gray. You visited it, but you have not yet processed it. When it leaves the stack, that's when it's processed. And you color it black. Also, the discovery time ends up being the first time that you see it and you put it into the stack. And the end or process time is going to be when it leaves the stack and you end up coloring it black. Right? And we're going to simulate the same thing that we did over here, but we're also going to keep track of this stack, at least for the first couple of iterations of this. Okay? So I'm going to go ahead and mark this as a 1. Oops. I want black. There we go. 1. And I'm going to end up coloring it gray. And my gray here is just going to be 1 slash, and then another slash here will end up being black. Okay? All right. And I've placed it into the stack. Now I look at the top of the stack here. I don't pop it off because I is not done yet, right? Remember, I got done at the very end. It was the last thing that we ended up processing on Friday. Right? So what I'm going to do is I'm going to go to the next node here. I'm going to look at the entire neighborhood, and I'm going to see that A and F are both white unvisited vertices. Now, if I go in a random order, of course, I could go to A or I could go to F. It doesn't matter. But if I go in lexicographic order and I'm consistent about it, what do? I push A, color it gray, and mark it with a discovery timestamp because now it goes into the stack. I'm going to speed it up here a little bit. I went to A, then to B, then to C, 3, 4, 5, 6, and 7. And all the while, these things were being pushed into the stack. A, B, C, D, E, F. There we go. I sped it up because this is the first time we're actually going to pull something off the stack. I'm looking at the top of the stack. I'm peeking at it, right? And I see that I've got F here. This is my current vertex, right? This is where I am right now. I look at its neighborhood, and I see a gray vertex, and all these are gray, by the way. Right, there we go. I see a gray vertex, and gray vertex. I don't see any unvisited white vertices. So what I end up doing is something different. I pop that off the top, right? I color that black, and since it's now left the stack, I mark it as processed, coloring it black, along with a end processing time here of 8. Right? Now what's at the top of the stack? Where I came from before, right? The breadcrumbs. These are my breadcrumbs along the way of discovery, all this stuff, right? So I go ahead and pop this off the stack. E, end time of 9. And now where am I? I'm at the current vertex of D. I look at its neighborhood. What do I see here? I see gray, gray, black, and black. Those are not the ones that I want to go to next because I came from them, or I already processed them and I don't want to process them a second time. So what do? I go to the next available vertex that's unvisited, colored white here. Right? G. There we go. Color that gray. I discovered it at timestamp 10. And then finally H. 11. And color it gray. Right? And that ends up being my DFS tree. Remember that we can create a DFS tree here. We'll talk about in more detail here in a second. But all of those edges that I colored as black are going to end up forming my DFS tree. Okay. What's this going to look like? Fast forward now. All I do is pop, 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 pop. And I'm all the way back at I, right, having the finishing timestamps of 12, 13, 14, 15, 16, 17. And when does the algorithm end? 18. How do I know that I'm done? The stack is empty. Right? Now you do have to be careful here. What if you had a graph that looked like this? I'm not even going to bother labeling the vertices. There we go. Now that might look like 3 graphs, but let's treat it as 1 graph. That each one of these is a disconnected component. If I do a DFS starting, say, here, what will it end up looking like? It might end up looking something like this, right? Did I explore the entire graph? Nope. What about these 2 components over here? These would still be unvisited white vertices, unvisited white vertices. So if you're going to do this stack-based data structure, the stack-based DFS, you may need to start over on another connected component. So keep that in mind. All right? Otherwise, let's write the pseudocode for the stack-based DFS. All right? DFS stack. All right? So my input will simply be a graph G. Right? And so my input here is an undirected graph G. By the way, what happens if you have a directed graph? Before we go on, maybe? Where's my digraph? Right there. There we go. What would a DFS look like here? For example, what if I were at B and I wanted to consider the neighborhood? Would I consider this edge right here? Would I consider this edge right here? Nope. Why? Because they're incoming edges. Right? You can't from B, you can't take this edge and go back to A. They're directed. So my neighborhood with respect to a directed graph is simply going to be the outgoing edges, these 2 right here. Okay? So another technicality. So my input is going to be a directed graph G, and my output is going to be a DFS. Output is going to be a DFS, depth first search traversal. Okay. So I need to initialize everything for each x in, let me give v comma e vertices and edges. For each x in v, I'm going to color x white, which is the same thing as unvisited. There we go. That's my initialization. I'm going to start my counter at 1 because that's what my counter started at here. Right? It's just going to keep track of the discovery time and the end time of all these things. Right? And I'm going to initialize an empty stack. Empty stack. I never checked the audio. Yep, it's good. I'm going to keep my hat on, though, because it's cold. Or at least my office was freezing. Right? All right, so I'm going to do an initialization here. I'll push the start vertex in V onto S. And by the way, what should my start vertex here be? Does it matter? No. Whatever criteria, here I did I's to make it interesting. I could have done something completely different, right? If I wanted to, I could do a completely different DFS, say, starting at A. And then I would end up going to B, then C, then D, E, F, backtrack, all the way over here to G and H, and then backtrack all the way back to A, and then backtrack, then visit I. Actually, sorry, no, what am I doing? From here, I would have F. I would have gone over to I because it's DFS, depth first search. So it would have resulted in a completely different DFS tree, possibly different discovery and finish times for things, etc. Right? So what's your initial vertex? Whatever your criteria is, right? 0, right? If you're doing the assignment this for next Friday, I will mark S with V, sorry. V with start time equal to counter. Right. I will color V gray because it's been placed into the empty stack. Right? And then I'm going to go into my main loop here. I'm going to go ahead and go up over here and give myself some more room. But otherwise, all this is the initialization. That's just my setup, right? Actually, all of this is my setup right here, okay? Here's my main loop. While my stack S is not empty, I'm going to do the following. I'm going to increment my counter plus plus, right? Because each time I make a step forward or I take a step back, I'm incrementing my counter and using that as a timestamp for discovery or finish times, right? And I'm going to look at what's on top of the stack. And we'll go to say X here. X will be S dot peak. So remember what peak is, right? You're looking at the top of the stack, what's there, right? What's at the top of the stack, but you're not popping it, you're not removing it, okay? This gives you your current vertex. Current vertex, right? That's the vertex that you're at right now. And then I will look at the next vertex. Next unvisited vertex in the neighborhood of X, okay? All I'm doing is looking at everything that's connected to X. I'm ignoring all the gray vertices, I'm ignoring all the black vertices, and I'm looking at the white unvisited vertices. And then what do I mean by next? Again, that's your criteria. You'd have to sort the neighborhood, or you would have to go through it and find the minimum or something like that, the next available one, right? Whatever your criteria is there. And then you have two choices here. If Y is nothing, right? In other words, no unvisited vertices, I will now start to backtrack. The way that we backtrack is by popping it off the top. S, oops, go back over here, S dot pop. Get rid of the current vertex and color it black. Process X, color it black. In other words, visited or processed. Right? Mark it with count. Mark the process time with count. And you're done. Right? There's you backtracking. Right? And now I've run out of room here, so I'm going to go ahead and go to the next one. Right? Dang it. Get rid of that and erase all this. There we go. Dot, dot, dot. Else. Right? Y is the next vertex. So what do I need to do? I need to push it. S dot push Y. Right? And color it gray. Color Y gray. That is visited for the first time. And then I will mark Y with counter. And it's discovery time. There we go. Come back over here. Yep, I did it. This, oops, it's too big. This should have been a vertical bar. There we go, all the way. Yep, there, like that. Right. So questions on that? Otherwise, in the notes, here's what I was working off of. I've got it annotated, and it's much, much nicer, right? So again, let's walk through this. Here's our initialization. We start our counter, we initialize our stack. We make sure that everything is colored white or unvisited, marked unvisited basically. You start at an arbitrary vertex by discovering it. That means putting it into the stack. That means marking it as gray, visited, and marking it with your counter. Right? And then all you need to do is, while your stack is not empty, increment your counter, right? and look at the top of the stack to get the current vertex. X represents the current vertex right now. Y is going to be the next white vertex, unvisited vertex in the neighborhood. And different criteria can be applied here to search for a particular order: lexicographic, least weighted, whatever your criteria is, random, right? Or like in your assignment, I think all of the vertices are numbered 0 through n-1. So go in numerical order, right? Unless you're directed to do something else, right? And then you have one or two choices here. If you still have deeper to go into the graph, then you go into it, right? You go deeper, as deep as possible. That's what this is. Visit the next unvisited vertex. Otherwise, if you've hit a dead end, well, what do? If you're in a maze and you hit a dead end, you start backtracking. Okay. Let's talk about efficiency here, right? Or other observations, right? So observations, right? Again, DFS may need to be restarted at unvisited visited vertices if it is a disconnected graph. And by disconnected graph, we mean a graph with multiple connected components, right? A graph with multiple connected components. Right? Some vertices are not reachable from any path. Right? Okay, and you can have that. You can have, I mean, just take a graph with n vertices and 0 edges, right? It's a completely disconnected graph. You start drawing edges, right? Then that starts connecting some of the things, but maybe not necessarily all of the things. This also tells you that you can use DFS to determine, given a graph G, is it connected or not? How many, if it's not connected, how many components does it have? How would you end up doing that? So, take a look. Did I erase that example? Nope. How would you, this has 1, 2, 3 connected components, right? How could you use DFS to answer the question, is G connected or disconnected? There's a graph that's connected. How could we use DFS to say, yes, it's connected? If you have to restart it over, right? If you do this algorithm right here, and at the end, right, when it breaks out of this while loop right here, right, if you still have unvisited white vertices, then like these over here or these over here, then you can say that it is disconnected. If all vertices are black at the end, right, that means that you process them all, right? And process them all, right? And so right there, right, they would all be colored black, and therefore, like in this example, right, once you do a DFS, they're all going to be visited. How do you answer the question if G is disconnected? How many components does it have? Right? So first of all, if it's connected, how many components does it have? 1. Right? This has 1, 2, 3 components. So how could you use DFS to answer this larger question? Do a DFS on this. You still have white vertices. Start over at, say, this vertex. You do a DFS on that, right? How many times have I had to restart the algorithm? Once, twice, right? And there's still unvisited white vertices. So go there. Oh, okay, now they're all visited. They're all colored black. And so what was my counter? 3, right? So all you have to do is DFS keeping a counter. This does raise an interesting question, though. Which one of these questions is more general? Can you use the answer, say that I've got an answer here, A, and I've got an answer here, B. Could you use the answer to one of these questions to answer the other question? Oh, okay. So if the answer A is greater than 1, then that implies that B, the answer there is what? Disconnected. Right? Can you work the other way? Question mark. What if I said, yeah, that graph over there is disconnected? Does that help you in determining how many connected components it has? No. You'd have to run it again, right? This gets into something that we'll talk about later. A difference between, say, decision problems. Decision problems are a yes or no question. Is this graph disconnected or connected? Right? Yes. Is this graph disconnected? Yes or no? Right? Then you also have, say, not functional problems. What I want. Counting problems. Counting problems. This is basically kind of like optimization. How many solutions exist? Right. Oops. Yeah. Right? So it's not just simply a yes or no question. It's how many. Right? Then you also have, say, functional problems. If disconnected, give me a series of sets representing each component. All right. More generally, I don't want to just know, does a solution exist or not? How many solutions exist? What I want is an actual solution, right? For example, let's go with the Hamiltonian path problem. A decision version of that would be yes or no, right? Yes, there is a Hamiltonian path. No, there is no Hamiltonian path. Versus, this is not what asked on your first assignment, but you could have probably programmed it. How many Hamiltonian paths are there? Right? Versus the functional problem here of, okay, give me a Hamiltonian path. Well, first you go from A to over to C, and then over to G, and then over to B, et cetera, right? Which one of these is most general? Can you use? Okay, so this is why I hate the terminology surrounding this stuff. This is all called reductions, right? And reduction always tells me that you're taking something complex and making it simple, right? You're reducing the problem. It means just the opposite, right? Can you use a solution to one problem as a solution to another problem? So could you use the solution to the decision problem to answer this problem? Nope. But you can the other way. Maybe you can go the other way if you're clever about it, right? If you start asking the right questions, right? For example, is this graph disconnected or not? It is disconnected. Okay, I'm going to take out one of the vertices and ask the same question again. Right? Is it disconnected now? And if the answer changes, that tells me something about the role that this vertex plays in all that. Right? That it's a cut vertex or something like that. Right? So this is a preview of what we'll look at the end of the semester when we look at computational complexity and NP completeness and stuff like that. But I always like to break it down into something that everybody does this in Computer Science 1. They just don't know it. What kind of a function are we talking about here? Something that returns a Boolean, right? True or false. What kind of function are we talking about here? Something that returns an integer, right? What kind of function are we talking about here? I don't know, a set of sets of something. If we're talking about Java, it'd look like something like that, right? So when you write functions and a function calls another function and that function calls another function, you're doing reductions all over the place. You just don't call it that, right? If you, for example, if you had to program any of this stuff, what would you do? Well, I would program this one, and then would you bother programming this at all? No. You would call this function, and if this integer is greater than 1, then you return this Boolean right here, right? So it's good programming practice to think of reductions, but most people don't think of it that way, right? All right, that was a little bit of a digression. DFS searches, depth first searches, can produce several artifacts. You can do what's called a DFS tree or forest. 1 R. It would only be a forest if it were a disconnected graph, right? And you'd have multiple components out of that. And within that, you can consider various categories of edges, right? For example, tree edges. These are edges that are directly traversed in the DFS walk, right? And I'm putting walk in quotes there. You're walking around the graph, right? You can also have what are called back edges. Back edges are going to connect a descendant in the DFS tree to an ancestor. We understand those terms, right? So let's go back to my example from way before Friday. Right, there it is. So we've got the ancestors. It's a family tree. Ancestors are up here. Descendants are down here. So if you've got an edge here connecting, like say I to F, right? Is that a back edge or is it a forward edge? Because you can have both, right? Forward edges connect an ancestor to a descendant in the DFS tree. But make an observation here, right? In an undirected graph, is there any difference between a back edge and a forward edge? No, it's undirected, right? So back and forward edges are the same, right? So consider it as a back edge. You can also have what are called cross edges. Cross edges, all other edges. Okay, so for example, something like this. This is what I left you with a question on Friday. This thing right here. Let me recolor it a different color. Could you have an edge like this between F and G? Let's look at the original graph, right? And let me clean this up. There we go. So F and G, where are they? F and G, there we go. Now, let's go through the DFS that we've been doing up to this point. I to A, B, C, D, E, F. At which point we started backtracking. But if this new edge were here, would we backtrack? No, where would we go? We'd go DFS, depth first search. Keep going as deep as possible, right? Oops. And that's just me going off there. There we go. All right. So where would we actually end up going? Over here, right? So is a cross edge something that looks like this or something that would look like, well, first of all, is that a cross edge? No, that's an ancestor of G, and G is a descendant of B, so that would actually be a forward or a back edge, right? The only time that we would have a cross edge is maybe if we had a different connected component. A, B, C, D, F, G, H, I, J. There we go. Over here somewhere. Or in the original graph, we had J sitting over here. Right? And it's in another connected component or something like that. Well, could we have a cross edge between, say, F and J? Let me go ahead and go with B, with a blue here instead. F and J. Let's come over here. F and J. Guess what? It wouldn't be disconnected anymore, would it? Right? So, in an undirected graph, in an undirected graph, cross edges are not possible. you only have tree edges and forward/back edges. What if you do have a forward edge? For example, we were able to go from I, A, B, C, D, E, F, G, H, all the way over here, F, and then we have this back edge over here back to I. What does that tell you about the graph? What do we have here? It's not a tree, and we know it's not a tree because that's a cycle, a loop, right? So DFS can be used for cycle detection, right? Okay. Let's see. Yeah, go ahead.
Why are cross edges not possible?
Well, here's your tree traversal here, right? If you have a cross edge that would go to another component, right, then that would be part of the tree. I would have gone to it. F to H, or F to G, was it? Which one was it? F to H is what I meant. Sorry. F to H. They're the two possible cross edges in the DFS tree, but then at F, we would have gone over to G and we've gone over to H, right? And then this would have been a back edge because F goes to G, goes to H. And so this is ancestor, grandfather, son, and grandson right here. And so it would end up being a forward or back edge. Right? So cross edges cannot exist in an undirected graph. Now, directed graphs may have forward and back and even cross edges, right, due to the orientation of the edges. And so that's why we do make distinctions between all four of those. Right? The cross edges would actually connect different connected components, or different connected components that you explored everything over here, and then you had to restart over here, but it's going across to something that's neither a descendant nor an ancestor, and so it's going across to another connected component. Right? And of course, each run of DFS may have a different ordering tree depending on your starting point. Right? And just simply using a DFS can get you a lot of stuff. It can tell you a lot about the topology of a tree, right? DFS can be used to determine if a tree, if a graph is connected, if it is a tree, right? Acyclic, etc. Right? It can be used or adapted for a lot of things. Really quickly here, what about the complexity? Right. It's going to be order what? Yeah, so 5-step process. What's the input? A graph. What's the input size? Input will be a graph. Input size? Yeah, size. What is the size of a graph then? It depends on how you represent it. Right? An adjacent, if it has n vertices, how big is your adjacency matrix? N by n, that's n squared. If it's an adjacency list, you have n lists, but the number of elements in the list corresponds to the number of edges. So it's actually order m, right? Or where m is the number of edges here, right? If you use a map, maybe it's n plus m, really depends, right? Sets, right? Again, n plus m there, right? Keep it simple, right? Input size, we'll just say it is v, which is equal to n, okay? Observation, what's the elementary operation? This is where we'll end it, and then we'll continue here on Friday. What is the elementary operation? Okay, so going from one vertex to another vertex. I like that idea. That means that you are traversing an edge. And every edge gets traversed maybe once, twice, or examined twice, right? What's another way of looking at it? All right, looking at a vertex and observing its color to see if I should look at it or not, right? So you said an edge examination. You said a vertex examination, right? Both of those are reasonable. Is there another one? Well, ostensibly, you're doing DFS for a reason, right? Where's my book? There we go. What's your reason? You want to process the data stored in the node. So there's a third option, right? Processing of data. Now, do you ever process a node more than once? Hopefully not, because then you're stuck in some sort of a loop, right? So the answer there would be order n, because every node is processed exactly once. And that might be your elementary operation. Right? We'll pick it up there on Friday.